Hi, this is the subject is artificial neural network, and the topic was given to me was Vapnik-Sherwan dimension, also known as VC dimension. I'll be explaining this topic with the three examples in the end. Before that, we'll come to the prerequisites. Uh, the most important is to know about what is hypothesis class. In machine learning, the hypothesis class is set of all possible hypotheses that you are searching over, regardless of their form. It is the set of possible classification functions you are considering. A hypothesis is a function that describes the target in supervised machine learning. The hypothesis that an algorithm would come up depends upon the data and also depends upon the restriction and bias that we have imposed on the data. To learn more about what is hypothesis class, we'll consider three figures which is shown in this slide. First and foremost, we'll come to the easiest example. As we can see in the top left of the as we can see on the top left of this slide, it states that there are number system where the points are on the blue points are on the left of B and the red points are on the right of B. If we consider a hypothesis class to separate these points, red points from the blue points, we can draw a point at point B, which would segregate the reds from the blues. This is fairly a simple example. Let us consider another example, which is here on the left bottom of the slide. Let us consider a two-dimension coordinate system where the blue points are on the first quadrant, as we can see, and the red points are on the other half. Let us uh, let us consider a hypothesis class where it includes all the lines, all the straight lines, which would be of the form y is equals to mx plus c, as we are considering two-dimension coordinate system. If we draw the lines as shown in the figure, we can separate the blue lines from the red ones. So it is easier. In the hypothesis class, we can see these lines can be included, which would serve the purpose of separating the blue lines from the red ones. Now, coming to the third, and which looks very complex. um the blue light the blue points and the red points um, are seems to be scattered all around, but if we try to observe it carefully, the the blue points lie between the circle, and all the red points lie above the red points of the circle. So if we consider the hypothesis class of family of circles, we can separate the blue points from the red ones. The equation for this family of lines becomes x square minus b, where b can be all types of ranges. And if we sign this function, all the points that are all the points that are away from the circle are to be red, and all the points which are inside the circle are the blue points. Now that we know about hypothesis class, it is time to understand what is shattering and what is shattering. So, an hypothesis class H is said to shatter set of points if and only if all the outputs for the particular data sets can be distinguished in all configuration by an hypothesis which belongs to the hypothesis space H. Now let us understand this concept in further depth. Uh, as we can see in the figure, uh, that we are given 3 points in two-dimension plane. Now, let us consider all types of possible configuration that might be of uh, of 8 possible outcomes, as uh, as it is a resultant of 2 to the power 3 that comes out to be 8. For first few examples, let us consider 3 points which are all blue. If we try to draw a straight line, if you have a hypothesis class of all straight lines, we can draw a straight line as shown in the figure, which would separate one half for all the blue points. Uh, for second figure, if we consider a configuration where all 3 points are red, we can draw a line on the right side of all these 3 points, and which will make all these 3 points in one direction, which serves our purpose. And furthermore, if we consider one more configuration where one dot is red and two blue dots, we can draw one line in between of these 2 points, which would separate the blue points from the red ones. So the hypothesis space seemed to work. The hypothesis space of straight lines seem to work. Um, if we go in a greater depth, we can see that for all 8 possible outcomes, we can draw straight lines. We can draw straight lines which would shatter, which would mean that we can shatter these 3 points in a regular two-dimension graph. So we know what is shattering now. So now we can come to the main definition of vcDimension, which is the VC dimension of the hypothesis class H is the maximum number of points that can be shattered by H. If H can shatter sets of arbitrarily large size, we can say that H has infinite VC dimension. Uh, to know more about VC dimension, we need to know that no sets of size greater than VC of H can be shattered by H, and there exists a set S of size VCH that is shattered by H. The importance of VC dimension is it informally works as a measure of model's capacity. It is used frequently to guide the model selection process while developing machine learning applications. We'll go through more examples to understand what is VC dimension and how do we calculate VC dimension. Infinite open intervals. The first example is where the space is all infinite open intervals, and the data points can lie anywhere between minus infinity to plus infinity. If we consider 2 points, uh, which can be of any configuration, blue or red, uh, so the total possible options can be 2 to the power 2, which is 4. As all 4 diagrams, as we can see in the slide, which might be 2 blue, 2 red, 1 blue and 1 red. Uh, so if we take the first figure here, we can have a point. The hypothesis space here we are considering is also a point, which can either be on the very left side of both the points or can be on the right side of both the points, which would result in shattering of these 2 points, which are all blue. And similarly, we can do the same for both reds. It can either be on the very right or very left, which would again shatter these 2 red points. If in case one is blue and one is red, we can have a point in between of these red and blue points, which would again shatter the points. Left side would be for blue in the third figure, and right for the red. Similarly, left for the red in the fourth figure, and right for the blue. From this example, we understand that VC dimension would be greater than equal to 2. It might be greater than 2, as it is sufficiently shattering 2 points by this example. But once we consider, uh, but now let us consider 3 points where the points are situated in such a way that two blue points is middle for the red point. So doesn't exist a single point where we can put the point so that it shatters the three given points in such a configuration. If we try to put the point in the leftmost, there's two blues and one red. in one category. So, and anywhere between the blues or the reds, we cannot put such a point that we can completely shatter this kind of configuration. So we can come to a conclusion that VC of H is not 3, and it can be maximum of 2. So uh, from conclusion, the the hypothesis space of one of a single point in a number system can only have a VC edge of 2. Now, coming to the second example, all convex sets in R square. Uh, if we consider all the points, the hypothesis space to be convex set, which might be a triangle, uh, which might be a square, a rectangle, a pentagon, or might also be circle. Since circle is a polygon with infinite sides, uh, so we are now clear with the hypothesis space. Now let us consider an example where, as shown in the figure, we can see there are a number of points situated in a R square, which is two dimension graph. Now, uh, if we try to randomly color these points in red and blue, as shown in the figure, we can draw a convex polygon which uh, which would separate the reds from the blues. Since there is no limit on how many number of points that we can put in this particular graph, so we realize the hypothesis space uh, completely satisfies all number of possible points. So the VC of H becomes infinite. Now we come to a third example, which is linear half spaces in R square. As we've already analyzed this kind of hypothesis in shattering concept that we learned earlier in this PPT. We have already seen that we can shatter 3 points before, but if we want to shatter 4 points, it's completely not possible for the given configuration, which means that linear half spaces in R square cannot shatter 4 points in a R square. So it is greater than equal to 3 or less than 4, then we come to a conclusion that VC of this kind of H would be equal to 3. This is the third example, and few more examples for the calculation of VC dimension is given in this slide, where VC dimension of KDNF would be K log n. VC dimension of axis aligned to rectangles in n dimension coordinate system is 2n. If we try to cross analyze this, if we consider two dimension coordinate system, axis aligned rectangles can only shatter 4 points, and 5 points shattering is not possible for any configuration of points in a two dimension. And if you try to extrapolate that for a three dimension where n equal to 3, the maximum that we can shatter is 6 by the logic of 2 into n, where n is 3. The VC dimension for half spaces that we have already seen in the example 3, where n equal to 2, which was two-dimension coordinate system, where VC of that kind of hypothesis is n plus 1, where for two dimension it was 3, where for three dimension it will be 4. The planes would be dissecting the number of points in a 3D space. Now, what is the use of VC dimension? Uh, to answer that question, VC dimension is particularly useful in analyzing the capacity of a learning model and determining its ability to fit various patterns in the data. It is used in model selection and generalization bounds and many more, but these two are the most important sectors where VC dimension comes into play. When comparing different learning algorithms or models, the VC dimension can help in understanding their capabilities. A model with higher VC dimension has larger capacity to fit complex pattern in the data. However, higher VC dimension also increases the risk of overfitting. Coming to generalization bounds, the VC dimension is used to derive generalization bounds, which are theoretical guarantees on how well a learning algorithm is expected to perform on unseen data. These bounds provide insights into the trade-off between the size of the training set and the expected error rate of the learned model. Overall, the VC dimension provides the quantitative measure of the expressive power of the hypothesis space and helps in understanding the generalization properties and limitation of learning algorithms. It um, enables theoretical analysis, model selection, and development of bounds on generalization errors, contributing to the field of statistical learning theory and guiding the design and evaluation of machine learning. To conclude, I would like to brief about whatever was understood in this PPT. To start with the prerequisites, we learned about what is hypothesis class. It is a collection of equations which tend to serve a purpose. Where here in machine learning, we try to classify a number of points, mainly used in binary classifications. We went through a number of examples to understand what is hypothesis class. In the first example, the hypothesis class were a number of points in an open interval. Here in the second example in 2D space, this was straight lines which was segregating blue points from the red ones, and the third was quite complex, and the hypothesis class here was a family of circles which was separating the blue from the reds. We understood what was shattering with an example of 3 points in a two-dimension plane where these 3 points are said to be shattered by a hypothesis H, where in this case, which was single line, which was able to shatter all possible configuration, which was numerically 8, as we can see in this particular diagram. This hypothesis space is able to shatter all the possibilities which can be arise from this particular arrangements of 3 points. Uh, Now we came to what was the actual definition of VC dimension, uh, which was maximum number of points that can be shattered by H. We came we went through example number one, which was infinite open intervals. We took the VC dimension for we saw if we can shatter 2 points using 1 point, which was completely possible. But later we understood that it was not possible for 3 points. So we came to a conclusion that VC of this particular H will be 2. For second example, we went through a convex set in R square where we took a lot of data sets. We distributed that in blues and reds, and even then we were able to segregate the blues from the reds. So we came to a conclusion that VC of H would be infinite in this case. Uh, Lastly, we went through example which was already quite explained in the shattering concept, where we were able to shatter 3 points in R square, but we are not able to shatter 4 points in R square. Which from that we can derive that VC of this kind of edge would be 3. We went through the formulas for uh, popular hypothesis, which is KDNF, axis aligned rectangles, half spaces, etc. And lastly, we know that it is very useful to estimate upon what can be the complexity, what are the capabilities of a machine learning algorithm. So that was all for VC dimension. We went through 3 examples, and thank you for your patience. Thank you.